Hello, welcome to another hilarious episode of Descriptive Differential Dynamics, where there's discussed an approach called a second course to differential dynamics. After the usual linear curriculum or introduction through school to the methods of analysis, where real analysis is often also just called analysis, and that dynamical methods or dynamical modeling is what's called using analysis for real world problems, solving problems, and that the differential essentially reflects those functions that are functions of themselves over time, with regards to things that accelerate or decelerate or grow or accumulate or diminish or attenuate. And they're descriptive in pretty much all sorts of related rates and equilibria and anything else that's in after a system of formula and equations. What is abstractly a milieu for what all can implement dynamical modeling, and that then the various fields of mathematics as are applied in it make for that they each have their strengths, and the point is to figure out how to lever their strengths in with regards to developing the sensible, fungible, and tractable what result making for this second course of analysis after having already kind of studied at least and earned the credits, as it were, up to Calculus 4 or a year or two of college mathematics in calculus, and then as well the usual surrounds of algebra and arithmetic, and then topology and function theory, that for geometry, and then for the linear algebra and the geometry and the vector spaces and stuff like that, but really again fundamentally geometry, and then this toposes and the functions and the relations in function theory, the things and how they are. This is the idea of this descriptive differential dynamics. That it's dynamic in the descriptions and it's dynamic in the differentials. With regards to the continuum mechanics is dynamics, and then with regards to statics and dynamics, that it helps to reflect how classically we have this static and central and the origin and the original, and then this complementary dual that helps explain the panoply of all what makes for arriving at these means and of the moments of the methods of the analysis. So about where we got to is we're almost up to harmonic means, and so about as far as all we've gotten up to the last episode too is averages, and so that's pretty much most familiar to anybody is a summary statistic, saying I get samples over time, I can take the average, and maybe it's just the average of the last two samples, or maybe it's the average of all the samples over time, how those develop modes and means and medians, and about the moments of their changes, where the means is kind of what they fall to and the moments is kind of what they shift on, the moments and means. That these are the kinds of things that go into making for our model. For the law of small numbers, these are the most recent few samples. And the law of large numbers, that over time these are all the samples. And that their averages so develop, and then that each one of those bounded windows has its own. It's just like sampling a real number between 0 and 1. That you first want to, and it's in binary. So first you want to find the place whether or not it's half or not is set, then whether a quarter is set, and whether 8 is set, and whether 16th is set, and through all the inverse powers of 2. So if those are all set, then it happens to equal 1.0. And if none of them are set, it equals 0.0. So as you sample these real numbers and you get into it, then you have expectations, none of the next value of the sample, 0 and 1. But there's yet that over time, if there is a tendency, then that will kind of show up. And these are the kinds of things that then make for models of that, as similarly then for a model of sampling from real numbers and scalar values, which are either unsigned in magnitudes, and then whether there's some average or there's some measure and meter. And then for this, the sign, positive and negative, and if there's a centralizing tendency, or what is the middle or zero, and the other was just differences from that. That the idea is to help build up then for these ideas what happens in the laws of small numbers, what happens when there are various laws of large numbers that crest or that simply go out, and whether or not some of them come back around or not. What does that mean? It means that there's really some systems in the continuum dynamics where there is more than one law of large numbers. And so then for statistics and probability and sampling and all this kind of stuff, where the average is a perfectly great sample statistic, is to figure out that in the non-standard analysis that there exists at least some few kinds of special functions that have the properties that, though belying their finite inputs, still have real character at infinity. That infinity is in the numbers, or as part of the space between any two spaces. It's 0 and 1 is, in one sense, is 0 and all the way there, or infinity in another sense. That there's a notion of scale and a scalar infinity as a real thing. And this is where you to grasp this and consider it is one thing, but then also to relay it and communicate about it with other people, it has to be understood that there are many vagaries of definition and ambiguities about what's infinite, or treating it as a quantity in terms of our system of algebra and derived quantities, a value, an infinity, or infinitesimals, iota values, or scalar infinities, because without restricting the domain to like these are the settings of the description, that an infinity or an infinitesimal has no ambiguity or from it derived contradictions. That requires a careful attenuation of otherwise the rules of arithmetic and the treatments of quantities, their elements and memberships in groups, or as about the operations, about the uniqueness and distinctness of these things, that when we're talking about division and dividing by 0 and closing that operation and figuring out what that entails as a space or consideration of it as a realm, a world, in a domain, about the relations that so follow, that then we can consider this at once from in an unbounded sense, that it just for inductively what happens when it gets bigger and bigger and bigger and bigger, and ascribe it to that the quantity is a relation to the inference, and another one from the either side saying this is what makes its increments and this is what makes its partitions. That a whole of an infinity is partitioned down, and the increments go off to infinity, and according to induction never meet. And according to these parts, they are never increments. But the idea is to put together arithmetic made from addition and division up front, that in this manner there's a very sensible, composable and decomposable account of how the images of those two operations together form a real whole, a real unity between 0 and 1 with infinitely many points inside, that is, as a scalar thing, the same thing as points between a 0 and infinity. So then this is what's called non-standard, but it's also extra standard or super standard, because in a usual real sense that it has real analytical character for a conscientious mathematician means that it has to, and it never goes away. It's permanent, it's enduring, it's real. It's Platonic and abstract and ideal. It's mathematical, this object of the universe of the objects of mathematics, of a theory of a universe of all the objects. In a theory of everything, one would largely expect there to be an everything. And because it's not finite, if it were, then it would be closed, and finite and bounded. as is not, because relations between those and relations between those and relations between those finite bounded things are also things, so there's an infinity of them. So then the idea to figure out what is its real character is a regular course. And I've already had this kind of well established before trying to figure out this second course in descriptive differential dynamics, which is a survey. And then as well introducing some of these idée fixe, like this iota values, scalar infinity, sweep these three definitions of continuity instead of just one in the middle, three. Line continuity, or like Aristotle's field continuity, our standard Cauchy-Weierstrass and all that's formal and standard. Signal continuity, exactly as is implements signal engineering. It's a real thing. The line continuity describing what it has to be, the metrizing ultrafilter that's Jordan measure and making for revitalization in the doubling space and measure theory. Field theory, classical, let out, classical. Signal theory, much involved with this rough and smooth planes of Poincaré and Euclid, and the Dirichlet problem. So these various settings of discussions of modes of things in the continuum mechanics is already very well outlaid and put out with the line elements, path elements, with the metrizing ultrafilter, Jordan measure, line continuity, everything familiar from the field continuity, and the whole theory of continuous functions and all that, analysis writ large. Although here, the fundamental theorem of calculus, instead of the intermediate value theorem being from here's axiomatic set theory, making our descriptive objects the ordered field, and then we add an axiom that the least upper bound property is fulfilled, and then we add an axiom that is measure 1.0, that instead that's implemented in the line continuity by itself, and then that's used to remove the need for a stipulation or an axiom from the standard setting, those together, so formally and fundamentally, and so on, for this basically attaching this to path elements in the Jordan measure, regular, and this Dirichlet problem, at least these three different, pretty much replete definitions of continuity, all in the long line of all the expressions in real valued functions in a linear continuum, about set theory and about Cantor space, about square Cantor space, and about Cartesian functions and semi-Cartesian or Cartesian or non-Cartesian functions for function theory and topology. Three different continuous domains make for more is better, that their fundamental is expressly better in according to Occam's razor or Schaffer's lasers, rubrics of these types of descriptions. That I set out to study continuity and the foundations of mathematics 20 or 30 years ago, and so that's my opinion of what it is. But I don't really have to put much stock in my opinion because I put down mathematical proofs that it is so. So then I just can rely on those as enduring proofs. What is so? This readily informs opinion, which is good. So let's try to figure out some more about the harmonic mean. So we talked about the algebraic mean. Take the sum of n samples, divide by n. Or take this as adding a sample, then trying to figure out how to maintain that it's a summary statistic when you don't know how many samples there already were. This is not tractable. To keep an average, you need to know the count, because otherwise you don't know how much to weight the next sample at a time. But here is discussed, instead of saying just dividing, we have this division operation, this division. You remove a portion that's proportional to 1 over n, then 1 over n minus 1, then 1 over n minus 2, and dot, dot, dot. Is that still the same? Yeah, but at the same time, you can just kind of say, now we have a set weighted for this much, weighted for this many. It's a summary statistic in this way. It's a statistic of a summary statistic. That a statistic is any sample or any value derived from a sample, its value in statistics and probability theory. Probability theory writ large, and with its usual law of large numbers and describing and defining classical probabilities. Although about conditional probabilities, we got a couple of kinds of uncertainty or unknowns. There's Bayes and the central limit theorem, and all that is great, standard, and well known. And then there's Knightian uncertainty after Bayesian uncertainty, and then there's Jeffreys priors with regards to Bayesian priors. They have different, slightly, the properties about why this is so. And so they make for different kinds of composition of random variables as functions and statistics about the difference between parameters and statistics. Then that there are yet plain quantities in summary of statistics, and so on, with regards to probability theory and what they call validity of statistical hypotheses that then make for useful estimates with well understood bounds of expectations. So anyways, reading about this, we wanted to get up to the average arithmetic mean. We talked about the isoparametric theorem from this book by Cantor about geometric inequalities and how that there's used these bounds, that these are means of bounds and means of approximation and estimation to estimate the bounds. Not so much the statistical notion of estimates, but figuring out what are upper and lower bounds according to total ordering and the monotone. So here's the Mark isoparametric theorems for triangles. And so it's figured out that the maximum area for a polygon for a given perimeter is if it's a regular polygon. It fills in the most space. It's bounded the least. It has the least amounts of corners to not fill, vis-a-vis how it's built here, usually in a linear inductive manner, the isoparametric theorem, that this is where when you have the theory of spaces and points as opposite to each other, instead of points and then lines and then planes and then dot, 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 out to infinite dimensional spaces, you have that a point and a space basically start, and so it's a point and the infinite dimensional vector space, and that those come together for simplicity's sake, like between 0 and 1, same kind of thing. That this is a model of the continuum in as arising, simply, directly, arising from axiomatic natural deduction. How can that be, you say? How can it not be? It's in effect. So there's these isoparametric theorems and notions about how the bodies of proof can be approached and how the inductive proofs fit together and also are really as a constructivist approach without this entire bulwark of stuff from the foundations need be. It's axiomatic. They're then not only their place and mold in the Platonic universe of mathematical objects in their library of their axiomatics in Hilbert's Infinite Living Museum of Mathematical Objects. They're not only a model of that according to axiomatics, and they're not only all the models they fulfill in the Platonic realm, but they're also legible and sensible. And that makes things much more sensible, fungible, and tractable. Whereas with regards to otherwise what comes when the continuum mechanics arise, as in the foundations, then that equips everything after from that. So then a lot of other theorems can be written as from either side of the complementary duals. And then the stronger results about how they meet in the middle, and they have to meet in the middle to actually emit what would really be a full result, basically is that a limit exists from both sides. Limit from the left and limit from the right. And then what that means with regard to, continuous droit, discontinuous à gauche, cad lag, or ad cag, or this kind of thing. Then the descriptive dynamics, those are both the inductive scaffold and then that whether or not really, indeed, when Zeno's arrow reaches its mark, the mark was reached by its arrow. You can see that ends up being this meeting in the middle makes for that much more replete, conclusive, closed, besides the usual it doesn't not meet. Which is fine. So, two triangles, they have the same base and the same perimeter. And so this describes other methods to set up stakes, to set up a scaffolding, and then see one side fall in and see how the other one stands up. These make for different approaches. The first overall thing is sensible. For example, I can relate these exactly. These are the only qualities and properties that they have. Their sides and their angles. Here, that for triangles, either sides or angles defines it. That then it becomes tractable according to a method's proof was like, well, it can be shown that this kind of construction will come in this way and this in another way, and they'll be congruent or incongruent and fall the same or different, similar, different, part, meet. Establishing a binary, a case for decision and deciding a thing, that it is decided, so that for then it makes for a case for induction, and then induction runs out, and it's called a proof. I'm skipping ahead a bit because I'd like to get to the point about the definition of harmonic mean and how it's brought forward. So it's brought forward some interesting stuff about 16t squared and about the properties of triangles as being half of parallelograms. I felt I had a pretty good introduction to the language of mathematics. I've never got something in mathematics class and it later had to say like, oh, that's not the word for that thing anymore. They're all still the same words. Sine squared x plus cosine squared x equals 1. About the orthogonal functions, sine and cosine, one thing I've been trying to figure out about them in the trigonometry and trilateralometry, and with trigonometry is about the right angled and the Pythagorean, about the circle, and trilateralometry is take an equilateral triangle and unhinge it and roll it out, and then flip it over and roll it back up, and flip it over and roll it out, flip it over, roll it back up, flip it over. They both make and chart these same functions, sinusoidal, of wave motion, which is very, very present and usual and reflects essentially this act of rotation, and as well for triangles, this act of revolution. That then for the identities and stuff like sine squared plus cosine squared x plus cosine squared x equals 1, those are very familiar when I had much more facility with the identities of trigonometry and used them to solve exercises. And I was quite alacritous or good, I guess, is at these types things because I didn't have much else to care about, so I was able to fill my ready bank with those particular things and had them at my recall and was able to just crunch them out. So now when I see that in this sort of second course, then what I wonder is what do I need to know how they arrived at that, or how can I figure out the different ways it arrives at that, vis-a-vis that, it began as just kind of like, this is a fact. And it came out as like, this is how we derive this fact, and it's derived, it's proved. And vis-a-vis these families of these things that carry into it. So a lot of time when I read a book like this, where the author's got a lot of specialized knowledge and interest, and then he's laying out these usual kinds of courses for explaining these kinds of things, then I'd take it or leave it, kind of what they are, because it's all a matter of connecting it into the context of what settings that it apply to this whole universe of mathematical objects. And then both how fulfilling and complete they can be, and how simple and closed they can be. Because both, which is at once frustrating, because how can you have both when it's hard enough to get either, and fulfilling because actually there's nothing but one-sidedness without having a critical perspective outside oneself, as it were, or with regards to separation of concerns and the composability and decomposability of all things. Complementary duals, everything has one. This is a good quote from the author. He says, "A false proof of this theorem, theorem 16, given any n-gon which does not have all its sides of equal length, when it can construct another n-gon of the same parameter with all sides of equal length and with larger area." And he says, "I describe this proof as a false proof of this theorem is given below, one which the author designed and with which he once deceived himself. It is based upon theorem 12. Read it carefully and see if you can discover where it is incorrect or incomplete." So he says that since the sides are not all of length p over n, it must have at least one side of greater length than p over n and one of smaller length. Our first task is to show that we may assume that these two sides may be adjacent. When we have done this, we shall complete the proof by using a slightly modified version of sectioning or otherwise, showing that what would fill in would be like concave and peaked, convex and peaked right there. And I wonder what he might get into regress is like, well, they're not that much different, then they're not that much different, and they're not that much different. It's kind of like in delta epsilonics or something like that it's like, well, there exists something that much smaller, and it's like, yeah, but again, there's like a related rate question or something like that, which are back to Zeno's arguments and all this kind of thing. It's like, how can we expect that these two things with just each partition infinitely divisible don't all add up as one same thing? It's like, well, something that is a measure and meter about and outside of them. And so here, it's just kind of like when you take it out from this collection, these two loose sides, the odd ones, the ones on the outside, and figuring they sit together, and then thus that there's some way to show that they don't make up more contribution. There's still as well as way to show is like, well, what if they're all average? What if actually you started with a regular polygon to begin with? Here it's stipulated not so, but how can you know? Or what if like half of them are one length and half of them are another length? Then well, it's like you can't say you pick the longest and the shortest one. These are the kinds of things that would get into it. So, he talks about Heron's formula, and he makes quite a development. If we repeat this argument at most n-1 times, we shall obtain an n-gon with perimeter p and with equal sides. We'll have an area greater than that of G, which set up proof. He says here, the error in this proof lies in the reflection steps. It may very well be that the triangle ABC, for example, cannot be reflected in the perpendicular bisector of AC without AB prime intersecting CD, something which we cannot allow to happen. This reflection can be performed without such a difficulty, provided G is convex. Here he defines convex. Earlier I was asking, oh, well, if you're going to define the isoparametric theorem, where's defined convex? And so here he defines it. A plane figure is convex if the straight line segments joining pairs of points of the figure all lie entirely within the figure. So first you remember the definition inside and outside, a boundary or shape. I mean, that's kind of contrived enough as it is. And then this just kind of so follows. There are, saying this in the interior includes the boundary. For example, that is a square convex. Yeah. Then whether that's the boundary is essentially inside or the boundary is outside is also where things are convex and outward, which can only be so for circular curves, and the difference between like circle convex and square convex. A subtle distinction, easily lost here and not needed. Not necessarily subtle. So he says another theorem that we cannot easily prove is the regular n-gon has the greatest area of all n-gons with equal sides and the same perimeter. Then we talked about L'Huillier and Steiner, talking about the isoparametric theorem, second bookmark here, and about in combinatorial geometry or constructions. I mean, I've never really seen like a taxonomy or a cataloging of classes and approaches and sequences and iterations of classical constructions. But that's kind of what we see here in these things. We've got the reflection principle. Symmetry, as wide or as narrow as you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. Thus wrote Hermann Weyl, one of the great mathematicians of our time. This is a quotation from his lovely book, Symmetry, Princeton University Press, 1952. So here from Weyl, we've been reading the fundamentals of the analysis of foundations, the fundamental foundations of analysis from Weyl. And so when you talk about symmetry and how that's often used to frame like the continuity, and it's like it's symmetrical, meaning it's the same on either side. And so there's a reflection principle, and symmetrical, it's the same on either side. Something that goes across it basically is as it is on one side and as it is on another side. So then you get for Noether's theorems of invariance, it's like a symmetry implies a conservation. Conservation implies a symmetry. Here that's subtly distinguished by having this continuity laws to come over it. A conservation law and a symmetry implies a transition as across a continuum, and a continuum is called the continuum function, I suppose, equals 0. But the idea being then that is either side that adds up to 0. So it's about pseudo symmetries in a sense. It's a degenerate or deconstructive case, but it's a little bit thusly more general. And where for invariant theory, the Noether's theorem is considered very fundamental. Here's for more fundamental. Indeed, arguments based upon notions of symmetry are among the most powerful and elegant in mathematics. In this chapter, we shall examine the role played in the study of inequalities by the simplest kind of symmetry which a plane figure can possess, namely symmetry with respect to a line, which divides the figure into two parts, each the mirror image of another. Symmetry strongly influenced the art of early civilization. Its use in mathematics was begun by the Greeks, led them to their wonderful discoveries of regular polyhedra, tetrahedron, a cube, octahedron, dodecahedron, and icosahedron. In turn, the symmetries of polyhedra have been partially responsible for the creation of the branch of modern mathematics known as algebraic topology. He recommends this book, Geometry and the Imagination by Hilbert and S. Cohn Vossen, 1952. I appreciate Hilbert for his challenge and the Hilbert program and his problems, and at the same time, I kind of don't appreciate some of Hilbert, and but I'd read that book. I'd be interested in it. So what I'm looking for here, we got Steiner's symmetrization Dito's problem, Dito's problem, conic sections. So if we're talking about hyperbola and the ellipse, then I imagine soon we get into the harmonic, geometrical notion and reflection principle. So this is this major section in geometric inequalities that I'm just kind of skimming over, because about the x-center of these constructions and arrays and diagrams and markings, what make perspective and projection, about the principle of reflection, and geometry. As we get into hints and solutions for geometric inequalities, I imagine I'll have to find another definition of the harmonic mean. As in here I've reached the preferred solutions to exercises and learning exercises in this text and textbook. Harmonic functions. Well, then I suppose what I'll do is I'll study for myself to figure out and find what is the harmonic mean, and that this book then though really help break down what's going on with the arithmetic and geometric means about this. So the arithmetic mean is this average. Takes sum divided by the count. And so then this geometric mean is you take the product and then take the root as many times of that number, which, for example, you would take that number and take that power back to that power again. It would be the same as the product of all these numbers. Root and power are reverse and inverse and reciprocal. Division and multiplication, ditto. And then that with regards to the properties of these means, about how similarly when it showed for the isoperimetric theorem that these means are closest when all the properties, the values are the same, is about how when they buckle or vary is to figure out what goes on. Then in the deconstructive account and reconstructive, when you have other operations that otherwise describe these same in and back and about and around, how they make summary statistics, so they're computed and derived, but as it would be for statistics, summary statistics or derived statistics, not memoryless, or here memoryless, that these are the kinds of things that get into making for more definitions of means and general means, and then with regards to things like finding more methods about the harmonic and the nonlinear, and these other things, looking for a foothold in this otherwise very widely explored field to figure out how to handle the odd case which needs a kind of lever. Because otherwise you end up with the sensible and fungible and tractable, that it might have error modes or pathological cases, and then it's kind of stuck. But it might well be, it's like, hey, vis-a-vis these means, we can arrive at, for some moment, a particular well-defined and well-posed sense of real character, and then from that, so arrive at what you can call a completion to this kind of problem, and a solution for these kinds of problems that would help then be a contribution to mathematics. And so it's very far-fetched to ever expect that you discover something new to mathematics. It's always expected you find something new to yourself, and indeed to even have to relearn, and there's a constant problem of forgetting everything. Everything is always being forgotten. Because we have limited resources, and the natural, usual progression of biology and metabolism is to maintain it that way. So then it helps to have like this least grab bag toolkit of tools, and know how to use them to figure out how to make a jig from this set of tools and arrive at another tool that is ad hoc, or in a sense on demand. The point being that it's a learning exercise vis-a-vis the execution then. From days when a computer was a room full of stenographers on adding machines, and a lot of paper coming in and out, or that otherwise the execution is various as a commodity, and is variously available. And so then the idea is, again, for this kind of course, a descriptive differential dynamics, is to have a proper theory of everything, in a sense, even if that's detached from otherwise the axiomatics, and then know what it means in terms of, like, here's axioms and here's a model for a model theory of these things, a theory of their models, and what can implement them, or what one would be if one existed or not. And then that's in definitions, so that, and they're attached to natural language words because they reflect real things, as far as mathematics is successful at all, as far as any kind of logic and consistency is successful at all, that is real. And then figuring out what the methods suffice, and of course how to research things, how to look things up. That's the usual thing to figure out. And for resources and aids, the resources primarily are then one person can have all the resources they need, and the idea is to figure out how that a whole theory of theory can be simple enough that everybody can have one, and then that it kind of results that way. It's not that difficult to have enough fundamentals to be sure that one's entire body of mathematical knowledge is, as with regards to any other reasonable person's body of mathematical knowledge, purely mathematical knowledge, fact. It's true. And you can take it or leave it, and it'll be there when you get back. It's true. So anyways, that's been a great little book there. And so we're reading about geometric qualities. And for that, we had this elementary induction to number theory. And we're going to get back now to some more of the heat equation and this book on Fourier style analysis, I imagine. I got another book the other day on the Lie symmetries, Lie derivatives, Lie groups, Sophus Lie. And it's kind of a compliment to this series, this one by Stefani from some long time ago, I've had this book for a few months, or it's from the 70s, and then it's from this Springer, what do they call that? Graduate text in mathematics, And so that's the one I got is more like a publisher has a whole line of graduate texts in mathematics. So for any one of these particular styles or settings, they'll get together some PhDs and write them up. And then compared to something like the books that I find in mathematics that are more like the author put down a work pretty much by himself, where there's like a couple of these different ODE books that I've read, or as mentioned, or here and there and that, or like reading the other day Nagel and Newman, or this about Gödel, and other ones that are kind of, or like Boyer or something like that, or Motson Weaver, kind of in the same way, and they seem to like they put those books out there regardless. That's their interest, that's their field, compared to professional publishers setting up professional mathematicians to make professional books. It's not quite the same thing as a professional mathematician making the book. So I that's just kind of my attitude about it. But then also there's that it'll vary in terms of what content the analysis and the demonstration provides. And what opinions it may have or not have, and thusly, according to propriety, largely, what true opinions that may or may not reflect on the intended receipt are allowed, because economics and conservatism, vis-a-vis what could only generously be, and the reason for, because of a wider, fuller, truer context, or the kind of like from reading from the Path Integral book. There's a couple places the author explains that's like, if this breaks down, it basically breaks out, and then that it could be undefined behavior and circle back around, compared to the usual notion of horseshoes count in close, and that's something to figure out, because sometimes the less conservative or guarded opinion is less risky, is because the conservative guarded opinion doesn't even know about what's outside. So that's not to entertain the irrational. In fact, it's the opposite. But at the same time, anything that starts with only pure stipulations or axiomatics is inherently flawed. It's just a science until it's proven wrong. It is a science, but it's not scientific to say that it's true. To really get a theory of true, it has to be in a true theory of mathematical objects. This might start to sound contrived, but it makes for that really everything is science. And that's a reasonable setting, and you can have faith and belief in any kind of other beliefs, desires, and motivations which identify reasoning processes or the subconscious or anything like that. That's consciousness is personal, and it's abstract, and so it lives in the world of free thought. But still, when it comes to axiomatics and settings, they're limited by their definitions. So that's just when it comes to consensus versus completeness, or consensus versus a coherent kind of approach. I tend to feel that I fit in a consensus of people who prefer a coherent approach. Prime number theorem. As x goes to infinity, pi x over log x goes to 1. Chebyshev's inequality all right, so that's said for today. This is a pretty brief and boring episode of descriptive differential dynamics, with the idea being that there's means and means and means, and so there's the arithmetic and geometric mean, and then there's algebraic means and the golden mean and phi and the golden ratio and this kind of stuff, ratios and means. Then there's to be figured out what are moments and what are means, and how and why are they kind of related, and why are they duals. I really like to better understand in all terms of moments and cumulants and orthogonants and linear algebra and how to deal with moments. And where moments are points of change, kind of like the moment of inertia, or the lever, as it were, of things that go around, vis-a-vis the lever of things that go up and down. That these are the kinds of things I feel like I'm missing in the definition, because such a notion is so central, like the idea of the moment. And like its indication is like a pause, but then as it's coming and going from that, or otherwise what a moment is. Then in terms of the means, and the means being kind of how high the river is as it all flows. What is the average? What is the characteristic of the number that would make it unchanging to compute it again and next the other one? Is it another property of the means that it's the same as you throw in as what you get out? And these kinds of things. And what are like the non-means and the non-moments, anti-means and anti-moments, these kinds of things. So I've kind of come up with an idea fix to approach means and moments as these complementary quantities. But I'm not really sure if that's justified. But I kind of feel that I have an affinity for it. I feel that they have an affinity for each other in terms of fulfilling each other, that they meet in the middle halfway, in the middle of nowhere. And thus in that manner, from pulling them apart from either side, the induction holds up, and that the induction is complete with regards to each other. Because then the idea that there's not one without the other is a very, very comforting sort of close to the dialectic and the square of opposition, to make for that the dialectic isn't just an argument, but it's also a theory, and these are the kinds of things that make for a very well reasoned approach to that. For example, for arbitrarily posed tests and examinations of critical reasoning and critical thinking, or what is the right answer given statements of fact and conditions, that it's never wrong. Because first you want to be always right, but then at the same time you can't. It also has to be never wrong. So again, kind of like the difference between and I hesitate to use the words conservative and coherentist or consensus and vis-a-vis the, say, linear and nonlinear, is it's got to be both, because one way without the other is not never wrong. It's got to be never wrong. Besides that either one is always right, then that's in a world where things that are right and wrong, it's relevant that there's both. So here that was framed basically about the zeros and the is the limit only well defined. Everybody learns the theory of the limit, that it's never not close enough, but that it meets its mark. The arrow is that it's from the left and from the right. It really does make the case for that, for the fundamental conception and the definition limit itself. It's as to where that it's not never wrong in terms of that's attached to other stipulations in for measure theory. That's least upper bound property in measure 1.0 above set theory stipulations of like irregular infinity and that's all the baggage, that all the axiomatic set theory that makes for a model of what's called real analysis has. And so it is short that one fuse or light bulb, and that makes a case for why that the complementary dual of this of increment and division proves that arithmetic is decomposable. So I'll just leave it at that in terms of then that otherwise, but so then that makes it so that there is an infinity. Because otherwise it's not, and there isn't. Hey, have a great day. I should so hope that life, courtesy your diligence and work and dreams and good luck and happenstance and circumstance and fortuity, get what you wish for.